Well, welcome everyone to our fall webinar. My name is Evan Barry. I'm the Executive Director of Energy Connections Canada. Thank you for joining us today. There's 160 of you on the call, so we have a heck of a timely and important topic to discuss today. There'll be a few of us speaking. I'm going to introduce Ishrat Oishi in a minute, and then Shannon Wong. Also following Shannon will be our speaker, Janel Wageman. But if you're interested in asking a question during the webinar, feel free to use the Q&A question button at the top of the screen, and we'll process and respond to questions accordingly. I'd like to begin by thanking our sponsors for their contribution to our efforts in 2024. Our sponsors are who make events such as our webinar possible. So again, I want to extend our appreciation to these sponsors for their contribution over 2024 and look forward to welcoming more sponsors in 2025. So thanks folks for enabling us to put on webinars like this for our members. So it's my pleasure now to introduce both our moderator and the individual who will be facilitating the Q&A afterwards. First up is Ishrat Oishi, who will be introducing Janel. Ishrat is the president and CEO of the Young Energy Infrastructure Professionals. YEIP is a nonprofit coast-to-coast professional association for early career individuals in the Canadian energy industry. She's involved also on the ECC Board of Directors and works closely with us on energy transition matters. In her day job, Ishrat works as a project manager at TC Energy, where she managed facilities integrity, high-impact mechanical repairs, and inspection programs in Canada and the US for TC Energy's oil pipelines such as Keystone and Grand Rapids. She also worked in the Coastal GasLink pipeline project and in capacity and other growth projects for TC. Now, in her current role at the Pipe Integrity Engineering team, Ishrat helps maintain the integrity of critical infrastructure and keeps gas moving. Also not in her bio, but I will add that in 2024, Ishrat was awarded the Emerging Leader Award at the Global Energy Show earlier this year. So I definitely want to remind folks of Ishrat's many accomplishments. Now, handling the Q&A for the session later is Shannon Wong. Shannon is currently in her third year of electrical engineering at the University of Calgary. She's been involved with YEIP for 3 years in various roles. Shannon is now the president of the YEIP UC student chapter, where she helps bridge the gap between students and the energy industry. In her free time, Shannon enjoys bird watching and playing violin and piano. So with that, it's my pleasure to turn us over to Ishrat to introduce our webinar speaker today. Thank you, Ishrat.
Good afternoon, everyone. It is a pleasure to welcome you to YEIP and ECC's first technical webinar of 2024. Shannon, give me a thumbs up again if you can hear me. Can you? Okay, good. Like Evan said, YEIP is a professional association for early career individuals in the infrastructure segment of the Canadian energy industry, and we do many networking events and webinars such as this one. And it is my pleasure to introduce Janel Wageman to discuss the topic of pipe integrity design. Janel has a mechanical engineering degree from the University of Western Ontario and has over 3 decades of experience in the oil and gas industry. Starting her career in Ontario with Union Gas, Janel has worked for numerous EPC companies across Canada before joining TC Energy in the construction and commissioning excellence team. Her expertise includes natural gas for vehicles, facilities planning, operations, engineering, construction, and pipe integrity. Outside of her day job, Janel has volunteered at a local school in Jamaica. In the past 15 years, she has done many fundraisers, and now the local Jamaican village has a community center and a rural primary school, and the rural primary school has a library. I think I speak for many young professionals like myself, and we are deeply inspired by Janelle, her career in the energy industry, and her social responsibilities. One of YIP's mandates is to advocate for effective energy infrastructure and to accelerate a sustainable energy future. And when we think about the business, the function of pipe integrity engineering and design is critical for the business to ensure we maintain our critical energy infrastructure and we keep gas flowing. And when we think about young professionals and our growth and stewardship within the industry, in that case, pipe integrity is the space where we pretty much get to learn and work on every key aspect of a pipeline. We are doctors of the pipeline. I'm very excited for the presentation, and I know I will be ready with pen and paper to take down some notes. And I know you are excited for the presentation too. Without further ado, I am going to pass it over to Janelle.
Well, thank you very much for that introduction, Ishrat. It's my pleasure to be here with you today and to kick off your webinar series. So when Ishrat asked me to do a talk, as a design engineer in the pipeline integrity world, I thought, okay, well, I can talk about this task and that task that I do, but that's really just talking about what I do. And I thought, more importantly, we need to discuss why I do the task that I do. And to understand the why is to look at the high level of what is integrity. We need to look at the 40,000 foot level and then work our way down to what do I personally do. And so that's how I'd like to structure the talk, is to generalize and then come down to specifics. So we'll start off by saying, what is integrity management and what is the program? We'll discuss 3 layers of pipeline integrity, the 3 stages of prevention, 3 main detection avenues, internal inline inspection tools that we use, and an example specifically to what I do would be with regards to the a pipe wall thickness transition design. And then we'll follow that up with questions. So at TC, our most important job is keeping our pipelines and facilities safe. That is an all-encompassing statement that everything that I do in my work is founded on this statement. Everything is for the safety of our assets. So the company's integrity management program is in place to help prevent, manage, and mitigate issues that could affect public safety, the environment, and the reliability of our assets. So this is a really big statement. So we're going to talk about prevent, manage, and mitigate further into the presentation. But what issues are we talking about? And basically, issues are leaks. Those are our issues. We deal with high pressure containment, pipelines and facilities, and our issues are leaks. So, excuse me.
Hey, Janelle.
Mm-hmm.
I believe that an error happened when the meeting launched. Can you try resharing your presentation?
Oh, you can't see any of it?
Yeah, it looks like it disappeared on us.
Oh, I'm so sorry.
Oh, no worries. No fault of yours. I think it was the meeting having a bit of a day. There we are. We can see it. You're good to go.
Okay, guys. All right. So we already talked about the agenda. So let's just go to this one. So issues are just leaks. So, and I don't mean just, but that's what we're going to be talking about. If you have a small leak at a valve that's above ground, then we're losing product. We're losing our inventory. Those are dollar signs just going out into the air. So you don't want that. That natural gas is also going into the air and the environment. We don't want that. And most importantly, if the leak is actually a rupture, then because natural gas has a high potential energy at the pressures that we're talking about, a full release, a rupture, is obviously very, very dangerous to anybody that's around. So that's the key driver, is we maintain our assets so that people are safe that are in and around. Pipeline integrity safeguards the pipeline and all its components. What do we mean by components? I'm talking about all the valves, elbows, flanges, everything to do with an assembly that is part of a pipeline. So your crossover valve assemblies, your launcher and receivers, all of that is necessary to make sure that we have no leaks. And the way we do that is we've split it into 3 layers. So integrity prevention, or sorry, pipeline integrity is, the first layer is prevention. Then there's detection, and then there's mitigation. So the first layer of protection against leakage is prevention, and that's pretty obvious. We want to prevent a leak before it happens, and so this involves actions and solutions to that we work through. And so we have design and construction practices that prevent leaks, operations and maintenance practices, and as well as ongoing training and education. So let's just talk about prevention for a second. We know that when we brush our teeth, we're trying to prevent cavities. When we change the oil in our vehicle, it's because we want to prevent it from seizing up. So there's things that we do in our daily lives that we do in order to prevent situations. And there are a mountain of things that we do ahead of time within the design and the maintenance, things that we do in order to prevent leaks. So I've got this nice pipeline picture here. So I'm going to talk a little bit more in detail with regards to prevention, and but I just want to talk about the documents, the rules, the regulations, and everything that we follow in the design of a pipeline. So pipelines are designed and constructed to codes regulated by the government, industry standards, and company specifications. So I want to talk about that a little bit more. With regards to government, sorry, I got such a dry mouth. With regards to government, you start off at the federal level. So you've got the CER, or Canada Energy Regulator. They have documents that are their guidance, not guidance, I mean, like they are thou shalt documents that we adhere to. And one of them is the OPR, or the Onshore Pipeline Regulation. Then beneath that is your provincial regulators. So in Alberta, it's the AER, or the Alberta Energy Regulator. And they have pipeline rules and pipeline regulations that we then follow. And then you would have your county. And if you're putting a pipeline through the county, you would need permits that the county would put in, extra additional things that they want you to do to incorporate into the design. And then finally, you have a landowner, and the landowner might have specific requirements that they want us to adhere to during design or construction. So we are responsible to a whole variety of stakeholders, from the very top, from the federal government right down to landowners. We are, like I said, responsible to all these stakeholders. But then there's other documents, the industry standards, and there's a whole suites of these. The CSA, Canada Standard Association, has a whole number of documents with, specific things in it that we adhere to. And then there's also ASME or ANSI. All of these, standards are documents that we design to. And then finally, our company specifications and TESS, CT, Gen, GL, pipeline construction spec, one that's near and dear to my heart because I still maintain that document. And that document has even additional requirements, even above what's in CSA Z662 or, in OPR. Like we tend to go a little bit above and beyond through various experiences and such. So let's just talk about this picture for a second here. So if we look at number 1, I'm just kind of pointing out that we've got coding here, and that's one of our first lines of defense for corrosion protection. And so this pipe is coated with, it's called FBE, fusion bond epoxy coating. And so if you imagine the pipe is bare at the coating plant, they blast it to get all the scale, just get it nice and smooth. And then they heat it up, and then there's a hopper full of the powder, the FBE powder. And there's it's got it's ionized, I guess I could say. Anyways, it bonds through electrical process and from melting, and it creates this very good protective layer. So prevention, again, against corrosion. Number 2 is indicating it's called an anode, a sacrificial anode. And it's about maybe 2 meters long. It looks like it's longer, but it's kind of cut off just where the dirt is on either side. So it's made of a material that corrodes faster than the steel. So it could be made of zinc or magnesium. And these 2 metals are bonded together electrically with cables, and they create an electrochemical situation. And so by having the zinc anode deteriorate faster, it in effect saves the pipe. And then these wires are then brought up to the surface, and this little above ground test station, the operator can open it up. It's shown as open right now, but it's generally closed. And they hook up their probes, and they can see the potential energies of both the pipe and the zinc anode. And they can tell whether or not it needs to be replaced or if it's still doing its job. So these are a bunch of things that are done in order to prevent, CP issues, corrosion issues later on. Detection. Constant monitoring of operation conditions are crucial to avoid any unwanted release of product. There are 3 main ways to evaluate the integrity or condition of a pipeline. So the first is hydrostatic testing, and I'll go into a little bit more detail with regards to when and where testing is done. Direct assessment of the pipe, and the use of internal inspection tools. So let's talk about this picture for a little bit. At the forefront here, this is called a test head. And this is the pipe that they're going to be testing. Now, in this situation, this pipe, after being pre-tested, is going to be installed with a technique called horizontal directional drilling. So we pre-test the pipe because after you pull it down into its position underneath a river or underneath a highway, it's certainly a lot more difficult to deal with an issue at that point. So we want to know if we have a problem with a weld ahead of time or with the material. So there would be a test head at one hand and one at the other, maybe a test cap at the other, maybe not a full unit, just a smaller one. But you fill it up with water and then you pressure test it up, and then it's got to hold for an hour without any drop in pressure. So we do that, as I said, as a pre-test in certain situations. Any new pipelines have to be pressure tested. And in the similar way that you're seeing in this picture, you would have test heads on either end of your pipeline. And you would likely have another pipeline coming towards me. So right beside it would be a test head if you're breaking your sections up. And finally, we do integrity hydrotests to verify the integrity of existing pipelines. So this is an example of what I would call anyways, a direct assessment. It was felt by the operator that there was water in the pipeline. He didn't know for sure, but he suspected that. That to me is a direct assessment right there. Like he's boots on the ground. He has this feeling that something's going on. So we needed to investigate it, and if there is, then to get rid of it. So this project involved cutting out a little section of pipe so that we could have this little borescope crawler go in, and there's hours of this footage, but he found that there was indeed some liquid in there, some water. And so then we just used foam pigs to absorb the water and to remove that. So I would call that a direct assessment, this using this little crawler to, yes, verify. You can see this nice girth weld in here too. So whenever I'm talking about a girth weld, it's when you join two pipes with a circumferential weld. Inline inspection tools are used to identify, locate, and measure anomalies. An instrumented vehicle is propelled through the pipeline and provides highly detailed information about the interior and exterior of the pipeline. Many types of anomalies are looked for, so changes in the shape of the pipe. We don't want dents, we don't want ovalities, we want as circular shape as we can get, right? We're looking for cracking, any manufactured flaws, metal loss, corrosion, and any kind of mechanical damage. So here's an example of some of the ILI tools that we use. Up here in the corner, this is called a caliper pig. And as it says, it detects shape. So right after a pipeline is built, the contractor and pressure tested and everything, like this is the last thing that he will do is do a caliper run. And so there's about 48 arms on the pig here, and these move up and down. And so they form to the shape of the inside of the pipe. So this here is an example of what the data looks like that comes from this tool. So you'll see two lines, two circles. The outermost circle here is what it looked like just before this feature, this ovality here. So these lines are constantly like moving in and moving out in real time if you were to watch it, and then you would see where it was above a threshold. And this one is 5.945% ovality, which is higher than the threshold that we accept by code, which is 5%. So we have to deal with that. So the way we deal with an ovality is by doing a dig. And so we remove all the overburden and the material that is in and around that feature. And what happens is it grows back into shape. By removing the load that's on it, allows it to reform back into its spherical shape again. And then we backfill and carry on. So that's what a caliper tool is. So it's very, very specific. It's somewhat low tech, you can see. Another kind of smart pig is an electromagnetic acoustic transducer, or EMAT, and this detects cracks. So they have permanent magnets and coils, sounds very much like a motor. But instead of moving something, the ultrasonic waves produced by these interferences move through the material. So in this little chart here, you can see that if there's no crack, it moves through the whole length of the material and back again. And so therefore it takes longer. And if there's a crack halfway through, for example here, it rebounds quicker. And so you can see where a little crack is located graphically. So they know exactly where to investigate that. So, and let's just talk about this last one, magnetic flux leakage, or MFL. I believe that these are either have it right above the material that you're wanting to see the thickness for, whereas the smart pig on what the purpose is will define what type of pig. So if you want to know more about the shape, you would use a caliper pig. If you want to know if you've got cracks, and then if you've got metal loss. So, and I think, maybe, I'm not even sure, but that there's combined pigs that, might do more than one, one task. So flow of information. So the ILI data is collected and evaluated, and you want to be sure that the data collected is really, really good and accurate information. So, data in, data out kind of thing. So one of the ways that we ensure that the ILI data is correct is we have what's called a calibration spool, and that's about a 6-meter length piece of pipe that has had defects machined into it. So obviously you're going to need a thicker pipe than this pipe on either side, because you're losing wall thickness by machining in these various defects. But we know exactly where the defect is located. So it might be a pinhole, it might be a little slot, and when the ILI tool picks up those spots, we can say, oh, yeah, the data is accurate because it saw exactly the location and the depth of this pinhole or this little, defect. So that's one way that we use to verify our information. And so then we review the anomalies, like all those little spikes and stuff. What is our wall thickness? Are we concerned at this point? Are these, SEC colonies growing? Like, it's always monitoring even past data to new data. You want to know, is it growing? Because it might not have been beyond threshold before, but now has it grown? So there's always also comparisons between old data and new data. So all this, data is reviewed, and then it's determined, well, what kind of repair do we want? We have a whole suite of different things that we can do to repair that anomaly depending on the severity of it. So finally, a repair method is selected. And that's where I would come in to play if the repair method meant, well, we need a cutout, so therefore we need a new piece of pipe. I get involved when anything with regards to materials, and it's going to be for a high pressure situation. So valves, like I said, pipe cutouts, anything where the procurement of materials for high pressure situations is required. So this is an example of something that I would actually do when I would be approached by the project that, hey, we need a new piece of pipe. So if you're thinking back to where we had that boroscope crawler, and so now we have a good chunk of pipe that had to be cut out in order to do the work that they did. So I know that that was MPS 20 pipe. And so I have this calculation sheet here. So 508 millimeters is 20 inches, which is also MPS 20 pipe. I would know that the existing pipe has a wall thickness of 6.35, grade 359. And when I went into inventory, and not me specifically, like others would provide this information that, hey, we got this, this, and this available in inventory. Which do you select? I might select this 10.5 because everything else was even thicker and thicker. So this might have been only the least wall that I could work with. But you can see that there's quite a difference here. And according to code CSA Z662, if you have a transition, like a difference in wall thickness of 1.6 or greater millimeters, you need to transition the beveled end. So that's why I'm showing a counterbore and taper joint design, which shows you how some of this material is cut away to make a nice weld between the existing and the new pipe. But we calculate out what is this counterbore length, L0. So that is a calculation because the highest stress point in this design here is right at this transition point where it starts to taper. So we want to keep this stress point as far away from the weld within machining capabilities, right? So that's why we define this L0. So this information would go to the fabrication shop that, oh, okay, we need to have a counterbore of 75 millimeters. So we've established what kind of transition point we want on either end, but then we also have to get this pipe pre-tested. So for example, it might be a 12-meter length of pipe. We send it to the fab shop with this calculation sheet. And this sheet would be stamped by myself. I would have another engineer check it for me, and then we would have our company permit to practice stamp on it too. So it's a pretty important document. Goes to the fab shop. They would look at it and they would say, oh, okay, I know that my minimum strength test is 8,100 and my maximum is 8,400. And those values come from right here. I'll show you quickly. So we know that our minimum test pressure for strength is 1.25 times the design pressure. So our design pressure is 6450, as you can see here, 6450. And you multiply that by 1.25 and you get 8063. And we just bump it up. So that's why you see 8,100 down here. Then we put, so we've established our minimum. We do have a maximum as per code, but we don't need to go that high. So we just put a cushion on there of 300 when it goes to the shop, and which means this is their minimum 8,100 and they can go up to 8,400. So they usually split the difference and add 150 to 8,100, and they'll start their pressure test at 8,250. And so they can drop a little bit, they can go up a little bit, but they'll stay within that range, no problem. I mentioned that we have different transitions, and this is an example of a back bevel design. And so you can see that the material is just cut here. There is no counterbore. It's just, machining just the end of the pipe. And I was talking about how there's stress at that transition point here. And this is a kind of a cool picture of a back bevel that failed. You can see the stress right at the weld there. And I guess that's all I have. We'll get into some questions.
Yeah, thank you so much, Janelle, for the presentation. It was excellent, and I learned a lot. I'm sure a lot of the audience did too. So we're now gonna go over some of the questions from the audience. I noticed that a lot of them are in the meeting chat. Feel free to also submit your questions in the Q&A section. Our first question is, what is the size of the minimum size of the crack that the EMAT can detect?
I want to say minuscule. I don't know what the threshold is, but it's very sensitive.
Another question. Oh,
yeah, because we're talking micro crack, right? Like you wouldn't even be able to see it. Like these are, very, very sensitive equipment. Go ahead. Sorry.
Another question is, how accurate are a lot of these tools? Should we do several runs and compare the results, or can one run of the tools detect all of the cracks?
So as I alluded to with regards to the calibration tool, that is one thing that we do to verify the accuracy of the ILI tool itself. These tiny pinholes that are machined into the calibration tool are really, really small. And the fact that they're being picked up at the exact proper location, really, really helps give us confidence that the tools are accurate. Plus, when you do digs and stuff, you also verify it. So we are constantly verifying the data. Let's, kind of say that too, but the tools are tremendous these days.
And we have a third question. It's wondering about the reason for behind tapering uneven wall thickness.
So this is in Z662. There's a lot of different diagrams of what you have to do to the end to prepare it to be to prepare it for welding. So that 1.6 millimeter difference is mandated by regulatory bodies. So that's one reason why we're doing it. But you also you want good fit up in the field when you're welding it too. So, with a tiny bit of an offset, and then you've got a little bit of wall thickness difference, these are accumulative. So we try to always have as good a alignment and match up in the field. So that's one of the reasons why we do different transitions. So I talked about the counterbore and taper transition as well as the back bevel. So the back bevel is more commonplace, in mainline when you're going from your line pipe wall thickness to at a road crossing. It might not be that much of a difference in order to require a counterbore and taper. It might a back bevel might be satisfactory, but this is something that we look at from a stress point of view as well. I mentioned that there was calculations that go into looking at like the length of that ligament, but there's also calculations that go in ahead of time that help you decide whether you can do a back bevel or whether you have to do a counterbore and taper.
Another question is, what is the most common failure mechanism you have seen in Western Canada?
I'm sorry, what is the most what?
Most common failure mechanism you have seen in Western Canada.
I don't know. I'm sorry. I'm not really sure. That would be more of a threat management question, I think. If I hadn't already, kind of impressed upon you folks in the first place that if this is the integrity pie, this is me, so there are other very smart people who could probably compile that kind of data for you. So I'm really not sure. Sorry.
We have another question. The presentation mentioned the importance of training and education to prevent the pipe failures. What are some of the mandatory certifications required for personnel involved in pipeline inspection and maintenance, and how often must engineers be recertified?
Yeah, so that's a really good question. Of course, we're always learning something new. We read something and it impacts us and it helps us to do our work better. But with regards to like official programs and stuff that we have in place, I can speak about one that I've been quite involved with in the past, and that is with regards to ensuring the qualification as per our TC qualification program for inspectors for hydrotests. So we have a plan where it's not a plan, but I mean, we have courses that individuals would take. They're in class and they're a whole day, and you become knowledgeable, let's say, about pressure testing. So project managers, project engineers, anyone who really cares can actually take that course. It's very basic, but very informative. And then, so our inspectors would also take that. They are most likely very, very experienced people, very knowledgeable people in testing for perhaps other companies, but we have additional safety measures that we put in place and different things that we look for when we're reviewing a package that they would only know if they took this course. So they have to take that course first. Then they have to shadow some, and I'm talking an inspector, for example, they have to shadow a certified inspector or qualified inspector to watch them fill out all the documentation and to understand those nuances that I was referring to. And then when they feel comfortable, they fill out all that paperwork, and that paperwork goes to our pressure testing SME, subject matter expert, who reviews the documentation and then will qualify that individual to do these tests at fab shops or in the field on their own. They don't have to shadow anymore. So it's a very rigorous program, and it's in place so that a person coming in from outside our company understands very specifically the requirements that we have for pressure testing.
We have another question. What are the key integrity factors that are considered when evaluating and selecting the pipeline coating?
The pipeline coating? Well, we have very, very good standards. I mentioned FBE coating, fusion bond epoxy coating. You can alter the thickness of that. You can, to such a point where if you want abrasion resistance coating, like it's a much thicker layer upon layer. So the coating itself nowadays is quite standard, but depending on your different scenarios, you might want different thicknesses.
We have another question for the digs. Are the digs executed prior to the acceptance of the final inline inspection report to verify worst performing features and the accuracy of the inline inspection data?
Sorry, can you repeat that?
Are the digs executed prior to the acceptance of the final inline inspection report to verify worst performing features and the accuracy of the inline inspection data?
So when we get the data and it's analyzed and it's determined that this particular location has features that are above the threshold, then it's also determined at that time whether to impose a reduction in pressure, a self-imposed pressure reduction. And so that would be the first line of defense. If you can't get out there quickly enough to deal with it, you would lower the pressure. So it's no longer a threat. And then you would go and dig it up. I'm not really understanding the timing of it, but we get the data, we've got decisions to make, and then we go out, and do it. And it might not just be a cutout, for example. That's maybe last resort. We have other ways to deal with features, thinning. So those are, wraps, that kind of thing. So a cutout isn't always, the only option. There are other options as well.
Among the different technologies presented, how does TC Energy determine what is or are the most effective inspection technologies? So for instance, inline inspection or direct assessment for different pipeline types and conditions, and how often does TC Energy perform these inspections to ensure optimal integrity?
Yeah, so pipeline systems have an established length of time between investigations. So for example, maybe one might be 7 years. This group of pipelines has to be reinvestigated every 7 years. So if you look at it from a program perspective, you've got all these various pipelines that are due for reinspection at various times. And so you can look at it all at one point, looking out, 5-10 years, you can kind of see how many pipelines you've got to investigate in 1 year. And maybe you've got a huge amount in 1 year and not so many in the year before. You can bring some of those projects forward as well. So at the very beginning, it's predetermined what packages of pipeline investigations are going to be done in any particular year. So all of that is, like I said, kind of predetermined and kind of worked out so that all the work in that year is kind of defined. So all the ILI run data, the analysis of it, the determination of what is going to be done, to filtering out to, okay, well, what materials do we need for the replacement, to the construction, and then finally, getting it back and operating. That whole process could maybe be a year from the time you get your ILA data to the completion of your construction, and then you're starting all over for your next year's program. So it's a yearly program that's very well defined as to what work packages are going to be dealt with in that particular year. And I think that you also asked, well, how do you determine what kind of tools you need? Again, it depends on what your situation or it depends on the age of the pipe, the type of coating, what kind of soil conditions it's in, what did the last results look like. Maybe you want to decrease the amount of time in between surveys. So it's something that we're always working with year over year.
The different methods mentioned in the presentation requires a very high level of collaboration with complex project management techniques. Could you please provide a high-level overview of one of the internal inline inspections from planning to completion? What is the duration of the end-to-end process, and how do you prioritize pipeline segments for inspection and maintenance based on risk factors like age, material, operating conditions, and external threats?
Yeah, so I think I answered a lot of that in the last question, actually. There's the program. We know how often each individual sections of pipeline need to be reinvestigated. So like I said, like every 7 years, this particular pipeline needs to be retested. So the retest might be a pressure test. It might not even be a tool, an ILI tool, because we can verify the integrity of a pipeline with a successful hydro test. That's one of the tools that we have available to us as well. So with regards to, what kind of tool, it's what situation are you trying to deal with?
There are about 5 minutes remaining in the presentation. If anyone has any questions, feel free to submit it in the chat. Other than that, just one final question. What are the emerging technologies and trends that will shape the future of pipeline integrity design and management? And could you provide a few examples of how TC Energy is staying ahead of their competitors in terms of adopting innovative solutions?
Yeah, well, I keep coming back to that calibration tool, because I just think that's just the smartest thing. Like anytime you can verify with using one method, the data that's collected in a different method, it's just it just enhances your confidence in that technology that much more. I'm currently working on a project where we've developed a prototype of a machined part, and we have had FEA analysis, finite analysis, done on it to map out where all the stress points are on this new machined piece that we want to be able to use. And in verifying the FEA data, we're doing a hydro test with strain gauges. So that is one source of data, which we hope will then confirm a different source of data. So, anytime that you can compare and therefore give yourself extra confidence that it's accurate is, I think, the things that we need to do more of going forward.
Thank you so much.
You're welcome.
So I think this concludes the end of our presentation and the Q&A section. I will hand it off to Evan to close off the webinar, but thank you so much, Janel, for your time and
You're
the
welcome.
excellent presentation.
My pleasure. Thank you so much.
And thank you, Shannon and Janelle and Ishrat on behalf of VCC for also joining us today and a very informative presentation. Appreciated the cutaway graphic and the photos of the break there. So I appreciate you took us from theory to practice during this discussion. So thanks again. I just want to briefly wrap. I'm sure if folks have further questions of Janelle, you could track Janelle down on LinkedIn. I know that's one method to get a hold of her for any further questions. Thanks again. I want to also remind members of our next upcoming event, which is featuring another Janelle. As it turns out, Janelle Benson of Pathways Alliance will be speaking at our November 26th AGM here in Calgary. So look for more information about that on our website. So thank you everyone for joining us, and to our speakers, moderators, and introducers for your contribution today.